Good afternoon, everyone. Welcome to another exciting episode of Dave Does Math from Home. Today we're getting into section 4.1. This is the start of chapter 4. We are done learning how to do derivatives, and it's time to start figuring out what kinds of cool stuff we can do with derivatives. We had a little taste of that in the last section when we did related rates. It's a great example of what we can do with implicit differentiation. When we don't limit ourselves to implicit differentiation, it turns out there's a lot of really cool stuff we can do with just regular normal derivatives. The most important thing we can do, and the thing we're going to talk about for most of chapter 4, is we can use derivatives to find the maximum and minimum values of a function on an interval or globally. The idea is you've got a function, it's doing something like this maybe. If you find the derivative of this function, it will give you the slope. So you'll get a negative slope, positive, negative, positive, negative. You'll have these slopes that are changing as x varies across this interval. In between these negative to positive things, you have points where the slope is 0. At these points where the slope is 0, it's usually 0 because these are the points where it's switching from negative to positive, or where it's switching from positive to negative. And at those points where it switches from positive to negative, that's where the function peaks. That's a maximum. And when it switches from a negative slope to a positive slope, that's when the function has a minimum. But all of these things are characterized by having a slope of 0. And we're going to use that to our advantage. We're going to look at functions. We're going to take derivatives of those functions. Once we have the derivative, we're going to set the derivative equal to 0. And we're going to find the x values that make the derivative equal 0, because those points are called critical points. The points where I shouldn't say m, I should say the points where f prime of x equals 0. All the points where the derivative equals 0, that's when the function has maximum or minimum values. And we need to talk a little bit about what maximum and minimum means in this context, because looking at this graph, I have labeled 4 things as maximums or minimums, and some of them are a little suspect. Let me make this more clear. So I think we can agree that this is probably the maximum. This is the highest point that this graph ever reaches as drawn. As drawn, I have heavy dots here because the function ends here and here. This is a function on an interval. It only exists from this x value to this x value. So I don't have to worry about what it's doing back here or what it's doing over here. It's just this. And this, I think we can agree, is the highest point on the graph. And that's nice. But I also said that this was a maximum. And it's clearly not the maximum, because there are larger points here. There's larger y values all over the place. So it can't be the biggest y value we have. So this guy right here is called let me call this A, B, C, D, E, and F. This point C we have here, we already talked about how point E is a global max. It is the largest y value you will get at any point in this function. So it's the global maximum. But C also deserves recognition because it is a local maximum, which means it's not the highest thing on the entire graph, but it is higher than everything around it. So if you only look at things that are near C, if you look at a very small interval on either side of C, this point is the highest that it gets in this neighborhood, it's called. that neighborhood of points around C, in that neighborhood of points around C, that's the highest point you get. So it deserves recognition as a local max. B and D, I think we can agree, are local minimums. They're not the smallest value on the graph, but they are smaller than everything nearby. F is the global min, because it's the smallest point on the entire graph, which is interesting because it's not where the derivative equals 0. Like, the slope isn't horizontal here. It's just where the graph ends. So we have to include that. And A we should also include as a local max, because it's an endpoint. So this is the basic idea. We're going to take these functions, we're going to find all the critical points by taking a derivative, setting it equal to 0, and solving for x. That's how we find these critical points. And then once we have all the critical points and all of the endpoints, like A and F, the endpoints of our interval, we can evaluate the function at all of those points and figure out what's the biggest and what's the smallest, and that's how we're going to get our maximum and our minimum. That's the basic plan. Let's do an example with an analytic function instead of a graph function, and we'll see what that looks like. Let's start with something pretty straightforward. We'll say f of x equals negative x squared plus 4x plus 5 on the interval from 0 to 6. So, some of you can probably guess that this thing looks like a parabola. It's probably a parabola that opens downward. We could find the zeros if we really wanted to and figure out where it crossed the axis. I don't want to. I'm not interested in where it crosses the axis. I want to know where it has maximum and minimum points. And to do that, I'm going to take a derivative. The derivative should be negative 2x plus 4. And I'm going to set that derivative equal to 0. And then I'll solve for x. Subtract 4 from both sides and then divide by negative 2. That will give me x equals 2. So there's only one critical point. X equals 0 and 6 are my endpoints. That was given in the problem. So I have 3 points that I need to check. There's 3 possibilities to figure out what one of these might be the highest nearby point, one of them might be the lowest, one of them might be some kind of local thing. We need to find out what's what. To figure out what's what, I need to plug these numbers into the original function. So I need f of 0. That'll just be 5. That one's easy. I need f of 2. That's my critical point. That'll be negative 4 plus 8 is positive 4 plus 5 is 9. And I need f of 6, which will be negative 36 plus 24 is negative 12. Plus 5 is negative 7. So, I collected my critical points, I collected my endpoints, I found the value of the function at each of these points, and this is telling me that this is the maximum, because it's the biggest number I have in this list, and this is the minimum, because it's the smallest number I have in that list. That probably means that this is a local minimum? That's my guess. Yeah, if it's near this 9, we have something that looks like this. So when x equals 2, we have 9. At x equals 0, we have 5. And at x equals 3, 4, 5, 6. At x equals 6, we have negative 7. So on this interval, this is my max, this is my min, and this is a local minimum. Local minimums are not super important on this homework. I think when we do this homework, it's basically just going to ask you for this information. But when we start doing the next section, which we're going to kind of slide very smoothly into, then this idea of this being a local minimum will be very important. Let's do another example. Let's see how that goes. Let's look at something hopefully a little more interesting. Let's do 1/3 x cubed minus 1/2 x squared minus 3x plus 1. This is the function. I don't know what this looks like. It's probably some kind of weird mass. Some sort of cubic, I don't know. Finding the zeros would be a pain because of all these fractions that are involved. But it probably does some wiggles. Let's do this on the interval from -4 to 4. And let's find the maximum and minimum value that this function achieves on this interval. First, I need a derivative. Derivative here should be x squared minus x Oh, I did this wrong. Did I? Stand by for one moment. I did this wrong. There we go. This is better. Okay. So let's look at the derivative of this thing. 1/4 x to the 4th minus 1/3 x cubed minus 3x squared plus 1. This is the function that I want to find the maximum. So, once again, this is now an even worse equation than I thought it was. It has several squiggles, and finding the roots and intercepts of this will be even more difficult than I said it was the first time I said I didn't want to do that. But finding the derivative and getting the critical points should be pretty straightforward. We need a derivative, so that'll be x cubed minus x squared plus, no, minus again, minus 6x, and then the derivative of 1 is nothing. So this is my derivative. I'm going to set it equal to 0 and solve. I have a polynomial, so I need to start factoring things. We'll take out the x first, and then we have x squared minus x minus 6 equals 0. Now we can factor this as x minus 3 and x plus 2 still equals 0. So my critical points I get from this are x equals 0, positive 3, and negative 2. And the endpoints should be negative 4 and 4. So there are 5 points that I need to check. And to check them, I need to plug them all into this function. And for that, I should probably get a calculator. I can start with f of 0. F of 0 is easy. That's just 1. F of 3 should be 1/4 of 81 is 20 and change. Minus 9 is 11 and change. Minus 27 is negative 16 and change, so negative 17-ish. I'm just going to do an approximation. Negative 17. I can find exact values if I had a calculator and or wanted to take my time with this, but I don't want to do either of those things. F of 4 should be 64 minus 21 is 43 minus 48. What did I say this was? 64 minus 21. Yeah, 43 minus 48 is negative 5-ish, plus 1 is negative 4-ish. And f of negative 2 should give me negative 2 to the 4th is 16. So 4 plus 8/3 is almost 3. So 7 minus 12 is negative 5. Plus 1 is negative 4-ish. And f of negative 4 should give me positive 64 plus 21-ish is 85 minus 48 is 37, 38. So I have a global minimum here. This is the smallest number we have. And I have a global maximum here. This is the biggest number we have. And I skipped a lot of the precision in evaluating these things because you all have calculators, you don't need me to do that in a video. When you're doing the homework for this, use a calculator. Make sure you get much more precise values than what I did. When we do a test or a quiz, don't use calculators because there's no calculators allowed on those, but the numbers will be more well behaved than this. I'm going to cut this video here and go to part 2. There is a part 2. Stay tuned.